Hello guys, today I'm gonna explain why for approximately 2 hours a day I look like a fucking Ninja Turtle. We are gonna talk about EEG foundational models and like the GPT era, as I called it, for EEG signals. In 2020, GPT-3 landed and completely changed our world. Suddenly, every natural language related task, for example, summarization and generation, solved by completely one pre-trained model. In my opinion, the same is happening right now, but for EEG signals. We are at the inflection point for EEG signals models. For 20 years, every brain-computer interface that was developed required few things: a bespoke model that trained on specific dataset with a specific headset. In my opinion, this era is ending, approximately 3 weeks ago. Today we're going to be breaking down a new foundational model called Zuna. We're going to explain what it is, and then going to experiment with our own data and see what this EEG foundational model is all about. Zuna is a 380 million parameters large-scale EEG foundational model. But before we talk scale, let's talk about how is it different from ChatGPT or BERT that you may know. GPT operates on something called tokens. Token is a word, subword, integer, etc. But EEG data is completely different. Think about like a continuous multi-channel data, like specifically like voltage data, from the different electrodes placed on your scalp. EEG obviously requires a new, different foundational approach that is different from the text and image generation we had so far. Zuna model offers us 3 main primitives I want to talk about and demonstrate today. First one is a situation of mask electrodes. Think, for example, that you have some consumer EEG device that offers only a certain number of electrodes, but you are interested in electrodes that are not located in the specific device, but might be interesting. For example, I use a Muse headband and I want to know what's happening on top of the brain or the motor cortex. The Zuna actually lets me do this using AI. Lets me like predict what was supposed to be like the signal in those areas, even though I didn't record it. Second thing is a situation of mask time modeling. Think EEG is very noisy. So think, for example, you had a time or a time slot where the EEG signal wasn't so good. For example, the subject moved a little bit. Zuna lets you actually predict or like extrapolate what happened during this time in the signal and let you get like the full detailed picture without the noisy data. The third thing is temporal reconstruction. Like think the model can actually learn and assess longer time frames and understand how the brain evolves during this time frame. These 3 primitives actually let us build amazing stuff and are revolutionary for the BCI landscape. First reason is cross-device normalization. Think that until now, as we spoke, every BCI application required its own dataset and headset. So for example, I couldn't transfer the knowledge from a BCI application done on specific headset, for example, a motive device, to another BCI application developed for Neurotech, which is obviously very bad because the data was limited. So this foundation model, using like the spatial awareness of it, the 3D spatial awareness on the scalp, lets you actually solve this problem and allow almost full transferability. Second thing is like cross-subject transferability. How can we move knowledge from different subjects, different head sizes, and different characteristics easily? So, foundation model sits between and let us transfer the knowledge. Third thing is like downstream classification. What I mean by that, think about all the applications you can derive easily out of this foundational model. Like in GPT, we have a base model and then it fine-tunes for specific tasks. Exactly the same thing happened in EEG data. We have this foundational model, but now if you want to classify, for example, emotions or stress, you don't have to train with these old machine learning trainers specifically for these use cases, for the specific population and dataset. You can generalize using the foundational model and then actually fine-tune it for your own task. So this is completely revolutionary. The consumer EEG device market is currently very, very fragmented, featuring a lot of different devices from a lot of different vendors and manufacturers. For example, some of you may know the OpenBCI devices, the Ganglion, the Cyton, etc. On another vendor is like a Motive or Neurocity, or maybe even this Muse. But each of these devices is working with complete different spec, number of channels and electrodes, which actually made the situation very, very hard until now to somehow develop applications for these consumer-grade devices. Not because the science is difficult, which is also true, but because it wasn't worth it until now for the developers and BCI startups to actually generate a unified version of software for all of these devices. This is about to change, thanks to these EEG foundational models. Now, I actually found the time to play with the new model, and it's amazing. I did few experiments. Let's talk about one of them. We did a one electrode reconstruction. So we gave it like a whole brain of a subject we did in the lab via the Muse 2, which is actually a low-grade consumer EEG device. And I actually masked the scan, the EEG scan, and gave it just like the frontal poles and the temporal lobes, and actually completely held the left temporal lobe from the model. So I gave it 3 of the 4 electrodes and wanted to predict and try to ask the model what happened in these electrodes in the meanwhile. So I will be able to actually compare. And the results are insane. You can actually see here this graph, which describing how good we actually predicted the brainwave of the subject in those electrodes per frequency. So you can see like a very, very detailed and very close reconstructions in the delta and theta bands of EEG. And like the higher the frequency, the lower the quality of the reconstructions. But for the lower frequency at least, almost identical reconstruction. This is very, very meaningful because it's not even trained on these low-grade devices. According to the actual documentation, the Zuna model was trained on 19 and up channels, and I actually gave it a try with 4 channels device and wanted to predict a non-existing electrode, and it actually succeeded. So it means the foundational model behind is very smart and evolving. But why I'm hyping so much about it in just a reconstruction? Because the reconstruction was so good that we can actually run like later emotion detection algorithms on these reconstructions and actually find meaningful stuff. And if we believe this missing electrode, we can actually ask the model what happened across the entire cortex of the subject. For example, I can ask about electrodes which the Muse doesn't offer. So for example, like top of the brain, the motor cortex, etc. And actually run my whole algorithm on hardware acquired by $500, which is a completely new revolution. So, as you may see, I'm super excited about it, and I might be from the very, very first to notice it. In fact, in my opinion, in a few years, we're going to look back at this moment, February 2026, and we will call it the GPT moment of the BCI landscape.